BGP is from 1994. It is the protocol that runs the entire public internet. And it works at a scale almost nobody expected when they wrote it. Close to 1 million prefixes, 100,000 autonomous systems, billions of devices behind them. In the next 15 minutes, I'm going to answer what BGP does to communicate between autonomous systems, to optimize path selection, to filter, and to scale. And we're going to look inside the actual BGP messages on the wire to proof. Here's our lab. 4 routers, 4 autonomous systems. Very simple. An enterprise, AS65001, 2 ISPs, Cisco PEA and AS200, Juniper PEB and AS300, and a Tier 1 transit provider, T1, as in AS100. The enterprise has a single edge router, CE1, dual-homed into both ISPs. T1 advertises 198.51.100.0/24 to stand in for the rest of the internet. Everything's pre-configured. From here on, you'll only see show commands in Wireshark, and we'll deal with 4 answers. So let's go. The first command we will run is show IP BGP, and then our actual subnet, 203.0.113.0/24. So CE1 originates this subnet. The path line just says local, and we can see that right here. That's Cisco's way of telling you that the AS path is empty because we made this prefix ourselves. So in other words, origin IGP. Local preference is, as stated, 100. So now let's actually see our neighbors. So show IP BGP to neighbors, and then we'll actually dwindle it down to subnets, .64.1.2, and then we'll do advertise routes. Here's exactly what CE1 is sending to our PEA, just our /24, which is the 203 network. Now let's watch that travel out of AS and across the internet. So in order to see these commands correctly, what we're going to do is we're going to clear our BGP sessions, which is going to force BGP to send update messages. So we'll get on PEA and we'll run the command clear IP BGP, and we'll do a soft out. So that soft clear forces PEA to re-advertise everything to T1. Same update messages BGP sent out when the session first came up. We're just doing this on demand for the camera. So this is the actual BGP update message PEA just sent to T1 over their eBGP session. So now what we're going to do is we'll filter for BGP, and then we'll actually see our update message. Now, if we expand this, we can see we have a few update messages. We see we have some path attributes, but this is more or less our next hop, which is in direct line. And our network layer reachability information is our 203 subnet, which is our customer edge, as we know. But we want to see out to the internet. So what we'll actually look at here is our BGP update message. And then we can see our network layer reachability information, which is 198.51.100.0. So what we're looking at is the origin IGP, the AS path, which in this case should be 200, and 65,001, which we can see here. 2 autonomous systems. The 200 is PEA's AS, stamped on the way out to T1. The 65,001 is the originator. Every time a route crosses an AS boundary, that AS at the boundary writes its number into the AS path. Every router downstream gets an authoritative record of which ASs the route has been through. That is the AS path, which BGP considers its most important attribute. It's the loop detector. If any AS ever sees its own number there, it drops the route. It's the tiebreaker. Shorter path usually wins. It's the audit trail. You can prove where a route came from. And it's all the topology BGP needs to share. The protocol doesn't try to know about routers or links. It just knows about ASs and paths. That's how BGP communicates between autonomous systems. The protocol carries the path itself on every update. So back inside of our PE term flows this Wireshark out. And if a customer edge now, and we look at our actual route out to the quote unquote internet, type this in, show IP PGP 198.51.100.0. Well, CE1 has two paths to T1's prefix. One path is via PEA, or AS path 200 and 100, and local preference of 200, which we can see here. That is our PEA path. And then our PEB path, which is our 300 and 100, that's our local preference being 100. Same destination, two ways to get there. So the asterisk right here says best via PEA. Why? Local preference. CE1 has a route map applied inbound from PEA that bumps local pref to 200, marking ISP-A as the primary outbound path. Local preference is the first tiebreaker in the BGP decision process, way above the path length, way above MED. You'll find that configuration on my GitHub when you download the lab configurations to build yourself. So what we can see here, if we execute a show run and then a section BGP, is we can see that our path preference is going to be prefer PEA in. So we actually built this route map. On CE1, what we'll do is we will stage this command for now and prepare ourselves to clear our BGP tables. I'll capture on gigabit 01 or gigabit 1, excuse me, and then filter for BGP, and then I'll run that command. And as we can see here in Wireshark, we receive messages instantly. So the soft inbound clears and sends a route refresh request to PEA, resends every update for this router, and we get to see them on the wire as they arrive. So here's the actual update, and what we're looking for is an update sent to CE1 for 198.51.100.0. So if we look here, we can in fact see that message. And we do see the prefix length and the prefix itself. So we again have the origin, IGP, the AS path, and this AS path is going to be attributes of 200 and 100. And our next hop will be PEA's interface. What's not in this update? Local pref. So local pref is IBGP only. It never crosses an AS boundary on the wire. CE1's local pref of 200 is set locally by the inbound route map that we just discussed earlier. The update just delivers reachability and the path. CE1's policy decides how much to value it. The full BGP best path decision is 8 tiebreakers deep, but you really only need 2 of them. Local pref is first, then AS path length to explain 99% of what you'll ever see in production. That's how BGP optimizes path selection. Each router runs the same decision algorithm, and the same path that wins is the one installed with the routing table. So now on CE1, if we look at a show IP BGP, we can look at CE1's full BGP table. It knows multiple prefixes, its own /24, depicted here, from both ISPs. If CE1 announced everything it knows back out to its ISPs, that would be called a route leak. The kind that took down Cloudflare, Amazon, and roughly a third of the internet for an hour in 2019. So we filter outbound. Watch. What we're going to do, we'll type show IP BGP neighbors, and then we'll actually specify an address 64.1.2, and then advertise routes. So all we see here is just and only r/24, not T1's prefix, not anything else. That enforced by 3 lines of config, a prefix list, a route map that references it, and a neighbor statement that binds the route map outbound. The prefix list says permit 203.0.113.0/24 and nothing else. The implicit deny at the end of every Cisco route map drops the rest, which you'll be able to see inside of the configurations once you download them. So now what we'll do is we will restage our BGP clear, but we will stage a clear out instead of in this time. And then as we do this, we get a capture backup between CE1 and PEA. So once again, we'll get a filter going for BGP, and then we will clear our BGP for that route. on CE1. Here's what just left CE1 on the wire. If we look at BGP update, expand the update, and we'll expand our path attributes and our network layer reachability information. So at this point, our NLRI contains exactly one prefix, 203.0.113.0/24. Without that prefix list, this update would carry every prefix CE1 knows. T1's prefix would be in there as well. PEA would re-advertise it, and other ISPs would believe AS65001 is now offering transit. That's the leak. The prefix list is the difference between an enterprise being a customer and an enterprise accidentally becoming a transit ISP for their own provider. That's filtering. One prefix list. One missing entry would be a global incident. Now the big one. How does this whole thing scale to 1 million prefixes? Back on CE1, we'll do a show IP BGP summary. And what we see here, CE1 has 2 BGP sessions, one for each ISP. That's it. The enterprise doesn't need to have a session with T1. It doesn't need to have a session with Google, and it doesn't have to have a session with every tier 1 in the world. It just 2 sessions to its own 2 ISPs. The ISPs handle the rest. That's the first principle. Hierarchy. Customers connect to one, ISPs connect to tier 1s. Tier 1s connect to each other. Nobody peers with everybody. The session count stays bounded. This single fact is why BGP has scaled from 25,000 prefixes in 1994 to about 960,000 today. The second principle is route reflectors. Inside an ISP, AS200, 300, or 100, every BGP speaker has to peer with every other BGP speaker over iBGP. That's a full mesh. 100 routers means 4,950 sessions. Doesn't scale. The fix is one router becomes a reflector. Everybody else becomes a client. 100 routers becomes 99 sessions instead of 4,950. Every real ISP runs route reflectors. The third principle is aggregation. Customers announce a /24. ISPs aggregate that /24 with neighbors /24s into less specific blocks where they can. The global default free zone holds around 1 million prefixes instead of tens of billions of individual hosts on the actual internet. And the fourth principle is the policy at the AS boundaries. Every AS decides what it accepts, what it announces, and how much it prefers each path. The protocol doesn't try to enforce a global optimum, it lets every AS implement its own business logic. That's what makes a telecom in Kansas and a telecom in Tokyo both work, even though they have completely different rules. Hierarchy, route reflectors, aggregation, and policy. 4 principles, 1 protocol from 1994. Bringing it back to the question, how and why has BGP scaled with the growth of the internet? Because it does 4 things right. It carries the AS path with every route, so any router anywhere can detect a loop by just checking for its own AS number. No global state needed. It separates the decision algorithm from the protocol. Every router runs the same 8-step tiebreaker but applies its own local policy, so policy is local, but routing is global. It lets every AS filter what it accepts and what it announces, so the burden of correctness is local. You don't have to trust the rest of the internet. And it builds a hierarchy. Customers, ISPs, tier 1s, route reflectors inside of each AS, so the section count and the route table both stay bounded, even as the underlying network grows by orders of magnitude. That's BGP from 1994, still running the internet. If you want lab files to reproduce this, the Cisco and Juniper configs, the Wireshark textures, and the topology, the GitHub link is in the description. Subscribe, and I'll see you in the next one. Thanks.